Okay, so once again, welcome back to another discussion which is all about elastic and inelastic collision. So, on the previous meeting, we've discussed all about the conservation of momentum as well as the momentum and impulse. So, for today, is we will be discussing all about the elastic and inelastic collisions. Okay, so let's start with elastic collision. So in elastic collision, the objects involved remain separate. So the total kinetic energy of the system is the same after the collision as before. So a perfect example for an elastic collision is the billiard ball. So after they collided, kung unsa ang ilang shape, unsa ilang form before the collision and after the collision, so they are still the same. And also, the kinetic energy of the system is the same before and after the collision. So walay na dungag, walay na kulang nga kinetic energy. So it is the same before and after the collision. So we have here the figures A, B, and C. So before the collision, let's say we have two gliders with springs. So during the collision, the kinetic energy is stored as potential energy in the compressed springs. So after the collision, these two systems or these two gliders has the same kinetic energy after the collision as before it. So kung pila ang ilang amount sa kinetic energy before the collision and after the collision, it is still the same. So again, walay na dugang, walay na kulang. So that is for the elastic collision. Now, whereas for the inelastic collision, it is a collision in which the total kinetic energy after the collision is now less than before the collision. So kung si elastic collision, the total kinetic energy is the same before and after the collision. For the inelastic collision, ang total kinetic energy na is lesser than before the collision. So we also have this what we call the completely inelastic collision. So for the completely inelastic collision, it is a type of inelastic collision in which the colliding bodies stick together and move as one after the collision. So let's say for example, again, we have these two gliders, but this time we put a Velcro on each glider so that when they collide, these two gliders will stick together. So we have here in figure B, now pag collide nila, the gliders stick together. It's because of the Velcro. And after the collision, maybe si glider A has a greater velocity than glider B. So, si glider A and glider B, or this system of two gliders, have the same final velocity. It's because pareho naman sila. They stick together naman. So, they have the same, or they move as one body after the collision. So, they have the same velocity, which is v sub 2. Okay, so here, let's look at what happens to the momentum and the kinetic energy in a completely inelastic collision of two bodies A and B. So because the two bodies stick together after the collision, so they have now the same final velocity, which is v sub 2. So instead of writing v sub A2 and v sub B2, we can have their final velocities as v sub 2. So they have now the same velocity because again, these two bodies A and B stick together after the collision. Okay, so now for the conservation of momentum, so we have here, this is the initial momentum must be equal to the final momentum. So this is the conservation of momentum. So on the initial momentum, we have mass of glider A times the initial velocity of glider A plus mass of glider B times the initial velocity of glider B is equal to, now for the final momentum of the system, we added the two masses of bodies A and B, or the two gliders A and B, times the final velocity V sub 2, instead of having VA2 or final velocity on glider A and final velocity on glider B, we can use V sub 2 as the final velocity of these two gliders. Okay, so suppose, for example, that a body of mass m sub a and initial component of the velocity va1x collides inelastically with a body with mass m sub b that is initially at rest. So which means na si vb1x, or the initial velocity of body B, is equal to 0. So from the previous equation, the common x component of the velocity, or the final velocity of these two bodies after the collision, will now be, we have this equation right here, v2x, or the final velocity of these two bodies, is equal to m sub a divided by m sub a plus m sub b times va1x. So this equation comes from this, the conservation of momentum na equation. But since VB1 or VB1x is 0, so this equation right here becomes 0. So that's why when we are asked to solve for V2, we will arrive with this equation. Okay, so how about for the initial and final kinetic energies of this situation? So for the initial kinetic energy, take note that kinetic energy is equal to 1/2 m times v squared. So the initial kinetic energy of the system is 1/2 m sub a times va1x squared. Now, asa man nga nung wala man si mass B here. Again, it's because the initial velocity of mass B is equal to 0. So if we add this here, 1/2 m sub b times vb1x squared. So again, vb1x is 0. So this one becomes 0. So again, that's why the initial kinetic energy of the system is just 1/2 ma times va1x squared. Whereas for the final kinetic energy of the system, we have 1/2, and then we have the sum of the two masses, ma and mb, times v2x squared, which is, again, is because after the collision, these two bodies A and B will become one because they stick together, or they move together as one after the collision. So now here, asa man ni siya gikan na equation. So this one is mo ni siya, which is from this equation right here. So we just substituted the value of v2x in our final kinetic energy na equation. So again, this one comes from here. So again, we just substituted the value of v2x as ma is equal divided by ma plus mb times va1x, and then we have quantity squared. Okay, so here we have an example of a completely inelastic collision. So we repeat the collision described in example 3, which we have discussed on the previous meeting, but this time equip the gliders so that they stick together when they collide. So let's say for example, we put a velcro on these two bodies so that after the collision, they will stick together as one, or they move together as one after the collision. So now here, find the common final x velocity, which is our v2x, and then compare the initial and final kinetic energies of the system. Okay, so here, for our given values, we have the mass of glider A, which is 0.50 kilogram. We also have the mass of glider B, which is 0.30 kilogram, as well as the initial velocity VA1x of glider A, which is positive 2 meters per second, and the initial velocity of glider B, which is negative 2 meters per second. Because again, negative, it's because the direction of the motion or the velocity of glider B is going to the negative x-axis. Okay, so now again, we are asked to solve for the final or the common final x velocity of these two gliders after the collision. Okay, so how can we solve for the common final x velocity? Okay, so we will be using the conservation of momentum equation for completely inelastic collision. So, take note that for conservation of momentum, we have m sub a times VA1x, or we have the initial momentum of the system must be equal to the final momentum of the system. So this is our starting equation. So here, for our initial momentum, we have m sub a, or the initial momentum of glider A, plus for the initial momentum of glider B, we have m sub b times VB1x, which is equal to, now for the final momentum of the system, we have the sum of the masses of these two gliders, MA plus MB, times V2x, because again, after they collide, or after the collision, they stick together as one, and also they move together as one. That's why they have the same final velocity. Okay, so now to solve for V2x is we need to divide both sides with MA plus MB. Okay, so that we can cancel out this one right here on the right side of the equation. So we are left with, now V2x is now equal to MA VA1x plus MB VB1x divided by MA plus MB. Okay, so let's continue right here. So again, V2x is equal to MA VA1x plus MB VB1x divided by MA plus MB. So substituting their corresponding values, we have MA, that is another example. Okay, so let's continue here. We have V2x is equal to, we have right here, MA is 0.50 kilograms times VA1x is 2 meter per second plus MB is 0.30 kilogram times negative 2 meters per second, and then divided by MA is 0.50 kilogram plus 0.30 kilogram. Okay, so now if we will calculate this one, we will find out that V2x is equal to 0.5 or 0.50, and then we have the unit meter per second. So this is now the final velocity of these two gliders, A and B, after the collision. Okay, so now aside from the final velocity, so we have V2x here is equal to 0.50 meters per second. Okay, so now we are done with the common final x velocity. Now the next step is to solve or to compare the initial and final kinetic energies of the system. Okay, so we will now solve for the initial and final kinetic energies of the system. Okay, so for the kinetic energy before the collision, or again the initial kinetic energy. The kinetic energy for glider A, we have 1/2 m sub A times VA1x squared. So we have 1/2 times MA is 0.50 kilogram times VA1x squared, or 2 meters per second quantity squared, which is, if we will calculate this one, we will arrive with 1 joule. Okay, so again, always remember na the unit for energy is the same as the unit for work, which is in terms of joule or joules. So let's proceed with the initial kinetic energy of glider B. So again, we have 1/2 mb times VB1x squared. So 1/2 times 0.30 kilogram times -2 meters per second quantity squared. So it is equal to 0.6 or 0.60 joule. Okay, so these are the kinetic energies before the collision. Now, how about after the collision? So after the collision, they have, or these two gliders have one kinetic energy, one final kinetic energy, which is K2. So K2 is equal to 1/2 times the sum of the masses of these two gliders, MA plus MB, times V2x squared. Okay, so again, we have 1/2 times 0.50 kilogram plus 0.30 kilogram times, we have our V2x is 0.50. So our V2x is 0.50 meter per second. Okay, quantity squared. Okay, so our final kinetic energy of these two gliders, or after the collision, is we have 0.10 joule. Okay, so notice that before the collision, the kinetic energies of these two gliders are 1 joule and 0.60 joule. But after the collision, it is now much lesser than the values of the kinetic energy before the collision. So now we know that for a completely inelastic collision, the total kinetic energy of the system after the collision is much lesser than before the collision. So that is for the initial and final kinetic energies of the system for this example. Okay, so let's proceed to another example. Okay, so let me erase this one. Okay, so we have another example, which is now an example of a completely inelastic collision, but this time in terms now of x and y components. So not only one-dimensional, but we are now dealing with two-dimensional problem. Okay, so a 1,000 kilogram car traveling north at 15 meters per second. So we have the car here on the along the y-axis, collides with a 2,000 kilogram truck traveling east at 10 meters per second. So we also have in our sketch here, the truck which is moving along the x-axis. So the occupants wearing seat belts are uninjured, but the two vehicles move away from the impact point as one. So the insurance adjuster asks you to find the velocity of the wreckage just after the impact. So what is your answer? Or what is the velocity just after the impact? Okay, so here, since we are dealing with, or since our objects or the car and the truck are traveling along both the x and y axis, So we will be solving first for the components of our momentum. So the components of our momentum along the x and along the y axis. But still, we will still be using the conservation of momentum, but this time along the x and along the y axis. Okay, so let's start with p sub x. So p sub x here is the momentum of the car along the x-axis plus the momentum of the truck. So let's have the variable c as for the car and t for the truck. So again, we have p sub x is equal to the momentum of the car plus the momentum of the truck along the x-axis. Okay, so for the momentum of the car, we have mass of the car times the velocity of the car along the x-axis, plus for the truck, we have the mass of the truck times the velocity of the truck along the x-axis. Okay, so mass of the car, we have 1,000 kilograms times the velocity of the car along the x-axis. Now notice here in our sketch that the car is moving along the y-axis. So our velocity of the car along the x-axis is 0. And then we have plus the mass of the truck is 2,000 kilograms times the velocity of the truck along the x-axis, which is 10 meters per second. So our momentum, the total momentum of these two, the car and the truck, is equal to, we only have 2,000 times 10 meters per second, which is equal to 20,000. So we have 20,000 and then we have kilogram times meter per second. So this is our momentum of the system along the x-axis. Now how about for the momentum along the y? So same procedure. Momentum of the car along the y-axis plus the momentum of the truck along the y-axis. So we have mcvcy plus mtvty. So again, we have the mass of the car is 1,000 kilograms times the velocity of the car along the y-axis, which is now 15 meters per second, plus we have the mass of the truck, which is 2,000 kilograms times the velocity of the truck along the y-axis, which is 0. So again, this one becomes 0. So we have 1,000 times 15 is equal to 15,000 kilogram times meter per second. So this is now our p sub x and our p sub y. So now, the next thing that we will do is to solve for the magnitude. So since again we are dealing with two-dimensional, which is the x and y axis, so we need to get the total or the total momentum na magnitude. So as you can see here in the diagram or in our sketch, we now have the value of p sub x and p sub y. So now our next goal is to get the value of the magnitude of the momentum. And also, after that is the direction, which is the angle theta. Okay, to solve for the magnitude, we will be using Pythagorean theorem. So, to solve for p, we have square root of p sub x squared plus p sub y squared. So, we have the values of p sub x and p sub y, so we can solve now for the magnitude p. Okay, so we have 20,000 kilogram times meter per second quantity squared plus 15,000 kilogram times meter per second quantity squared. So, our total momentum or the magnitude of our total momentum is okay. So we have here 25,000 kilogram times meter per second. So this is our magnitude. So now we proceed with our direction. So for the direction, we will be using the tangent theta. So tangent theta is opposite over adjacent. So let's go back to the sketch. So here is our angle theta. So the opposite of the angle theta is our P sub y, whereas our adjacent will be our P sub x. So we have opposite is P sub y divided by P sub x. So our P sub y is 15,000 kilogram times meter per second divided by 20,000 kilogram times meter per second. So our units on the numerator and the denominator will be cancelled out. So tangent theta is now equal to 15,000 divided by 20,000. Okay, so now to solve for the angle theta is we have inverse tangent or tangent inverse of 15,000 divided by 20,000. So our angle theta is now equal to, let's calculate, 36.8698, or we have 87, and then we have degrees. So we have now the magnitude as well as the direction of our momentum P. Okay, so the question here is we are asked to solve for, or we are asked to find for the velocity after the collision. So going back to the equation of momentum, we have P is equal to the mass times the velocity. Now, to solve for the velocity, divide both sides with the mass. So, velocity is equal to the momentum divided by the mass. Now, we have our momentum, which is 25,000 kilogram meter per second divided by, now for the mass is we will add the two masses, which is the mass of the car and the mass of the truck. So we have 1,000 plus 2,000, we have 3,000 kilograms. Okay, so cancel out the kilograms on the numerator and the denominator. So we are left with meter per second. So 25,000 divided by 3,000 is equal to 8.33 meters per second. So if you're asked what is the velocity after the collision, your answer will be 8.33 meters per second. Okay, so we are done with the inelastic collision. Now we proceed to, or now we dig deeper into elastic collisions. Okay, so for one-dimensional collision, let's say along the x-axis na elastic collision, the conservation of kinetic energy is given as this one. So the kinetic energy, let's say we have two bodies, A and B. So the initial kinetic energy of body A plus the initial kinetic energy of body B is equal to the final kinetic energy of body A plus the final kinetic energy of body B. And also, for the conservation of momentum, we have, again, this is the initial momentum must be equal to the final momentum. So we have the initial momentum of body A plus the initial momentum of body B is equal to the final momentum of body A plus the final momentum of body B. Okay, so now here we have the equations of the elastic versus the inelastic collision. So for the conservation of momentum, let's have it here as one-dimensional lang sa. So conservation of momentum, again, for the elastic collision, we have this one. And for the inelastic collision, our final velocities of our bodies A and B will now be as 1, which is v2x. Okay, as also for the conservation of kinetic energy, here is our conservation of kinetic energy in an elastic collision. And also, here is the conservation of kinetic energy equation for the inelastic collision. So as you can see, there is a difference between the velocities or the final velocities of the conservation of momentum and kinetic energy for the elastic and inelastic collisions. Okay. So for the elastic collision, we have this special equation that we can also use in solving problems regarding with elastic collisions, particularly with perfectly elastic collisions. So we have this equation right here. VA1 plus VA2 is equal to VB1 plus VB2. Or we have the velocity of body A, the change in the velocity of body A, we have the initial and final velocity of body A is equal to the sum of the velocity, initial and final velocity of body B. Okay, so how did we get into this special equation? So we will be discussing that in a separate video so that you can understand where it is coming from. But for the meantime, we will proceed with our example. So, example for a perfectly elastic collision, we have a 4 kilogram ball moving east at a speed of 5 meters per second, strikes a 2 kilogram ball at rest. So, calculate the velocities of the two balls assuming a perfectly elastic collision. Okay, so we have for our given, let's have m sub 1 as our 4 kilogram ball. M sub 1 is 4 kilograms. And then our m sub 2 is the 2 kilogram ball. And then we also have the initial velocity of the 4 kilogram ball, which is moving east at a speed of 5 meters per second or positive 5 meters per second. Now, whereas our initial, let's say V1, let's have it as V1I for the initial. V2I, it is mentioned here that the 2 kilogram ball is at rest. So, our initial velocity for this 2 kilogram ball is 0. Okay, so now we are asked to find the velocities of the two balls, or the final velocities of these two balls, which is si V1 final and si V2 final. So we will be solving for this two. Okay, so how can we solve for this one? Okay, so for the using the conservation of momentum, we have the initial momentum must be equal to the final momentum. So we have m sub 1 times v1 initial plus m sub 2 times v2 initial must be equal to m sub 1 times v1 final plus m sub 2 v2 final. Okay, so substituting their values, we have m1 is 4 kilograms. Our v1 initial is 5 meters per second. Plus, we have our m2, which is 2 kilograms. And our v2i is 0. So, on the right side of the equation, we have m sub 1 is 4 times v1f which is missing, still missing, plus M2 is 2 kilograms times V2F. Okay, so this one is 0. So we have 4 times 5. Let's disregard first the units. So 4 times 5, we have 20 is equal to 4 V1 final plus 2 V2 final. So notice that we cannot yet still solve for the V1 final and V2 final. So how can we solve for the V1 final and V2 final? Okay, so this is now the time to use the special equation, which is this one right here. Okay, so we have V1 initial plus V1 final is equal to V2 initial plus V2 final. Okay, so we will be using this special equation, or we will be using another equation for us to be able to solve for the V1 final and V1 initial. Okay, so our V1 initial is 5 plus our V1 final is still not yet, we will still about to solve for that, is equal to our V2 initial is 0 plus V2 final. So let's transpose V1F to the right side of the equation. So on the left side, we are left with 5 is equal to, we have V2 final minus V1 final. Okay, so this is now our second equation. Okay, so the next thing that we will do is we will now combine these two equations so that we can now solve for V1 final and V2 final. Okay, so we have here 4 V1 final plus 2 V2 final is equal to 20. And on the second equation, we have, so let's rearrange this one. We have negative V1 final plus V2 final is equal to 5. Okay, so negative V1 final plus V2 final is equal to 5. Okay, so let's eliminate V1 final first. So to eliminate V1 final, we will multiply this equation by 4. So that we will arrive with, let's rewrite the first equation. We have 4 V1 final plus 2 V2 final is equal to 20. And then on the second equation, it now becomes negative 4 V1 final plus 4 V2 final is equal to 20. So let's add. So this one will be cancelled out. So we are left with 6 V2 final is equal to 40. Okay. So V2 final, to solve for V2 final is equal to 40 divided by 6. So our V2 final is equal to 6.67 meters per second. So we are now done with V2 final. Now let's calculate for the V1 final na po. So we will be using this equation, this one, to solve for V1 final. So we have negative V1 final plus V2 final is equal to 5. So let's transpose V1 final and 5. Let's exchange them. So we have V1 final is equal to V2 final minus 5. So take note that V2 final is 6.67 meters per second minus 5. So our V1 final will be 6.67 minus 5 is equal to 1.67 meters per second. So now we have our final velocities of these two balls, assuming a perfectly elastic collision. Okay, so let's rewrite first again our V1 final is equal to 1.67 meters per second, and our V2 final is 6.67 meters per second. Okay, how can we know if the momentum is conserved as well as the kinetic energy? So let's recheck, or let's check if conserve ba si momentum if this are our final velocities. So let's have first the conservation of momentum. Let's check if the momentum is conserved. So using the equation for the conservation of momentum, we have m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. So let's substitute their values. M1 is 4 times V1 is 5 plus M2 is M2 is 2 times V2 initial is 0 is equal to, we have our M1 again is 4 times V1 final is 1.67 plus M2 is 2 times our V2 final is 6.67. So this one is now 0. So 4 times 5 we have 20. Now on the other side we have 4 times 1.67 plus we have 2 times 6.67, which is equal to 20.02. So meaning the momentum is conserved because 20, we have our answer is approximately equal to 20. So we have 20 is approximately equal to 20.02. So meaning the momentum is conserved in these two balls. Now how about for the kinetic energy? So let's try to use the special equation. So the special equation, again, we have the initial, V1 initial plus V1 final is equal to V2 initial plus V2 final. So let's check if we have the same answer, or we will arrive with the same answer on both sides of the equation. So V1 initial, we have 5 plus V1 final is 1.67. V2 initial is 0 plus 6.67. So 5 plus 1.67 is 6.67, which is equal to the right side of the equation, which is 6.67. Which means na our answers, or our final velocities of these two balls are 1.67 for the V1 final, and V2 final is 6.67. And also, for the perfectly elastic collision, the momentum as well as the kinetic energy of these two balls are conserved. So I think that is it for our discussion regarding with the elastic and inelastic collision. So thank you for watching, and we'll see you on our next discussion.